All right, hey everyone, welcome to Jeff's DSUA-111 Data Science for Everyone section for April 3rd, 2020. This week we're doing statistical simulations and hypothesis testing with the kind of overarching moral of the story being testing dice to see if they are phony, right? If they're loaded, right? So if you're at a casino or something, maybe not a casino, those are like regulated, but if your friend says, hey, play me in dice for $2,000 and they provide the dice, you might worry that maybe there's something up with the dice. Like maybe they don't roll a 1, 2, 3, 4, 5, 6 equally likely. Maybe someone put a little bit of weight on one end to make it so that 5 always comes up, or not always, but 5 comes up more than any of the other numbers, and then they bet on 5 all the time. So today we will learn a statistical technique, essentially, to test that a dice that you find is fair, by basically just rolling it a bunch of times and recording what rolls come up and then saying, okay, well, what's the likelihood that it would come up with these rolls if it was fair versus what's the likelihood that it would come up with these rolls if it was loaded, if it was weighted in some way, right, to have not even outcomes. So yeah, go to your, and I have one announcement, which is this one right here. Here, let me screen share. So I sent out an email 6 days ago, it looks like, on March 27th, with a Google form for, it will let you provide us with basically a summary of what your ideas are for your final project, right? Your data science project. And you can click it and you'll see that I'm making this announcement because I've only gotten like 3 responses. And yeah, I just want to highlight that basically right here, there's some links to data sets. If you haven't found a data set yet, but if you have, enter your email address, your name, and a link to your data set. And then I have specific questions like, what's your initial hypothesis, right? That's kind of the most important because I can't really tell if your data set is like good to use or not unless I know what hypothesis you want to ask about it. So if it's like a data set with countries in like a recording of countries' incomes in the year 2000 or something, but your hypothesis is like, oh, I want to see if, becoming a democracy increases income in the country or something. That data set's not going to let you do it, right? Because the data set only has observations for 1 year, 2000, whereas like you want to see change over time. So basically, like if you submit your data set and you explain your hypothesis, what a row represents, what are the columns that you want to look like, the sample that it represents, any potential biases, and then why you chose it, then basically I can just like give you feedback saying like, yeah, keep going. Maybe like, oh, here's a even better or simpler, easier to use data set that will let you ask the same question, things like that. So just like it's completely optional, but if you go and find that email in your email from March 27th, click the Google form. And if you can't find it, just like email me and I'll reply with this link. But yeah, it's completely optional, but I'm happy to look at it. I've replied to all the ones I've gotten so far and just like let you know whether or not it will work and like kind of like give you a summary of the next steps that you can take. Cool. All right, so but for the class now, make sure you go to DSUA-111.rcnyu.org and click spawn. I just did that. So this will come up and lab 6 should now be released, right? So you'll see released assignments, lab 6, you can click fetch. Now go down here to lab 6 and click to open the notebook. All right, so yeah, like I said, you're testing dice. you know, someone hands you a die, singular dice, and you want to be able to say, like, how can I use the tools I know from statistics and math to tell whether it's fair or not, right? So here, this table, you should get used to this kind of format of tables, because this is the standard way to represent like any probability distribution, right? You have like the thing that there are probabilities of, in this case, like face of 1, that what is the probability of the face with 1 dot on it coming up if you roll it? What's the probability of 2 coming up? What's the probability of 3 coming up, 4, 5, and 6? And then the next column gives you the actual probability, right? So in this one, it's loaded so that 1 comes up literally half the time you roll it, right? Even though a fair die would only be 1 out of every 6 times. And then 2, 3, 4, 5, and 6, all of those, they only come up 1 out of every 10 times, right? One thing to note is that these probabilities add up to 1, right? Because every time you roll, it's going to be either 1, 2, or 3, or 4, or 5, or 6. So one of those 6 is going to happen. Therefore, the probability sum to 1. So yeah, what we want to do is we want to say, okay, to do like any statistical test, what you want to do is you want to formulate a hypothesis, right? And specifically a null hypothesis and an alternative hypothesis, right? So the null hypothesis is kind of like, you know, how do I put it? The not interesting case. It's like the best way I can describe it. It's like the not interesting case, you know, whereas the alternative hypothesis is like, you would be surprised if the alternative hypothesis came true, right? Because remember, in science, it's kind of this inherently conservative enterprise where you're very much trying to like you're very surprised if you find something in an experiment that goes against your intuition, right? Like, it's not that your intuition can't change, it's just that like null hypothesis is kind of, okay, the, you know, normal case, and then alternative hypothesis is like, what would really make you, you know, break that kind of previously held hypothesis. So in this case, the null hypothesis is that the die is fair, right? Each face of the die appears with probability 1/6 when rolled. That's kind of the definition of fair. So the alternative hypothesis is that some faces of the die have a higher probability of appearing than others, right? So that's kind of what we saw above, is that a fair die would just have probability of 1, 1/6, probability of 2, 1/6, probability of 3, 1/6. And whereas a unfair die would just have, it would be different, right? Some of the faces would have higher probability and other faces would have lower probability. And I like wrote, you know, the rest of these hypotheses just to show you what is not appropriate, right? So this one I think is like most kind of, what's the word? It's the one I would expect to be picked the second most besides the correct answer, because it's like, oh, if the die is rolled 6 times, each face will come up exactly once. It's like, that, you should take note, is not a probabilistic statement, right? And so it should raise a red flag. It's saying like, that's like very deterministic. Like, you roll the dice 6 times and each face will come up exactly once. Like, that's, you know, right, probability is kind of messier than that, in the sense that like, oh, if you roll the dice 6 times, like actually 5 could come up 6 times, even if it's fair, right? So probability doesn't work like that. That's like a deterministic statement. The probabilistic statement is like, if you keep rolling the die, then on average, each face will come up 1/6 of the time, right? But that doesn't mean that 6 specific rolls will all be, you know, 1, 2, 3, 4, 5, 6. So that's why this one's not right, right? It's not true that like, if the die, even on a fair die, if you roll it 6 times, you might get 3 twice, 5 twice, and 1 twice, right? It's not that each face will come up exactly once. And then this one was just a little tricky because it's like, okay, even numbers will appear with probability 1/2, and odd numbers will appear with probability 1/2. Well, I mean, that's true of a die, but that's not really what we want to test, right? Like, actually, because if you think about it, that the die could, a fair die will satisfy that, but also there are unfair die that will satisfy that, right? So say there's a die and it's loaded so that only 2 and 3 ever come up, right? So imagine you roll a die where like 1, 4, 5, and 6 can never come up, and 2 and 3 are the only sides that can come up. This will actually still be true, right? Because the 2 will come up half the time, and the 3 will come up half the time. And so even numbers appear with probability 1/2, and odd numbers will appear with probability 1/2, but it's not a fair die, right? It's still a weighted die. So this is not kind of like detecting, this is not picking up what we want, right? Which is that all of them have equal probability. And so same idea with this one, you know, prime numbers will appear with probability 1/2, and non-prime numbers will appear with probability 1/2. That's also like, it's a true statement of a fair die, but it's also a true statement of a lot of not fair die, right? If you have a die where, let me think. Yeah, 4 comes up half the time and 5 comes up half the time, then this will still be true, right? Even though it's not a fair die, because 4 is not prime, and that will come up with probability 1/2, and 5 is prime, and that will come up with probability 1/2, right? So yeah, basically you focus. You want to focus on this null hypothesis, and then the alternative hypothesis is literally just like the negation, just like the not of the null hypothesis, right? So like the correct null hypothesis is that each face of the die will appear with probability 1/6. So then the alternative hypothesis is just not that, like any other distribution other than all of them are 1/6. Cool. So Q1 answer is C. Great. Question 2. So yeah, this is what I was saying at the very beginning, which is that like, all right, so we start to test it by actually rolling it, right? And again, we create one of these tables, like I just call this a proportion table. It's like an observed proportion table, I guess would be like the formal name for it, but it's just saying, you know, say you roll a die 5 times and you get 1, 2. The first time you roll, you get a 1. The second time you roll, you get a 2. Third time you roll, you get a 3. Fourth time you roll, you get a 3. Fifth time you roll, you get a 5, right? So then you can compute these proportions, right? You see these proportions, they're just like measured based on these outcomes right here, right? So 1 comes up in 1 out of the 5 slots, and 1 divided by 5 is 0.2 right here, right? So 2, it also comes up in 1 out of the 5 slots, right? So it gets proportion 0.2. 3 actually comes up twice, so that's 2 out of 5 total rolls. So then that's 0.4. 4, it never comes up, right? So that's 0 divided by 5 total rolls. 5 comes up once, so that's 1 divided by 5, and then 6 doesn't ever come up, right? So now what happens is here we have this function mystery test statistic, right? Which takes a table like this as its argument, right? So it's a function where you give it a table like this, specifically meaning like you give it a pandas data frame, right? You give it a data frame with 6 rows, each representing a face of the die, and the columns are face, meaning, you know, what's the numeric value of the face, and then proportion, which is how much did it come up when you rolled it, right? And so the idea here is you're supposed to look at mystery test statistic, and you're supposed to figure out what it does. And it's a little tricky. This is kind of, this assignment, parts of this assignment are kind of carried over from the data science class at Berkeley. You know, so they learned like different things in different order. So just in case you're confused, I'm just going to walk through it a little bit, which is saying, okay, so the first thing it does, so sample, right? It takes one, that's the one argument it takes, it's called sample, and that is just this table, right? So it's saying, roll your die, you know, however many times you want actually, and just create this table of the proportions that you got of each face, and it will compute some test statistic, right? We're not telling you yet, that's further down in the assignment. So it takes the sample, right? The first thing it does has nothing to do with the sample actually. It just creates an array that's just, this starts to look normal when you get more used to NumPy, but at the beginning, this can look very weird. So let's just break it down into like saying X is equal to 2 things multiplied by each other, right? So we'll multiply these 2 things and assign it to X, but let's focus on the 2 things in the multiplication one by one, right? So the first one is np.ones, and all that does is it makes like a big array of ones. So np.ones is just like, I want a list, right? I want you to create a list. I want you to create an array, right? NumPy has arrays, Python has lists, but it's NumPy, so I want you to create an array, but just make everything in the array a 1, right? Because then what we can do is we can multiply, right? So you have a list where it's like, however long your sample is, I'm going to like make an array with that many slots, right? However many sides there are of the die. And well, here, let me just write it out. I feel like I'm not explaining this well, but I have to do something here real quick to make it editable. Get rid of that. Now I can edit this. So I'm just making a comment that's saying like, so for a 6-sided die, this will make 1, 2, 3, 4, 5, 6, and I'm gonna multiply it by 1/6, right? So maybe that makes it make a little more sense, which is like, you just make a big array filled with ones, but then you multiply it by 1/6, right? Meaning like you end up with a thing that's like 1/6, 1/6, 1/6, 1/6, 1/6, right? So that is actually just the array containing the probabilities of each side if it was a fair die, right? So that's what this line is doing. It's saying X is just array of the probabilities of each face if it was a fair die, right? Now, Y, what it does, if you notice, now it's actually looking in sample, the argument that we gave it. So it's the table of what we actually observed the probability of each face to be once we actually rolled the dice. And it's subtracting it from X, right? So all that's doing, if you think about it, is it's saying like, okay, so X is like perfect. X is like the table that you'd get, right? It's the probabilities that you get for just a perfectly fair die. And now what this is right here, sample proportion, that's this column here. So that's like what we actually saw, right? So all that Y is just saying, take the probabilities we actually saw and subtract it from 1/6, right? So let's say sample proportion. Let's pretend like that's actually, well, let's just write what's up here, right? 0.2, 0.2, 0.4. So 0.2, 0.4, 0.20, 0.20. I'm actually going to write it as fractions just because it's easier to do math that way. So 1 out of 5, 1 out of 5, 2 out of 5, 0 out of 5, 1 out of 5, 0 out of 5, right? So this, again, this is, remember, the probability, perfectly fair, what the probability of each face would be for a perfectly fair die. But now this is the probability of the faces that we'd like infer based on what we saw, right? We'd say we rolled it 5 times and we got a 1 time. We got a 2 1 time out of the 5. We got a 3 2 times out of the 5. We got 4 0 times out of the 5. We got 5 1 out of the 5. We got the value 6 0 times out of the 5, right? So now all that Y is it's just subtracting. Yeah, all that Y is it's subtracting these, right? So you take the sample proportion, right? So you take the actual probability of ones in the actual rolls, and then you take what the probability of ones would be on a fair die, and you just subtract them, right? So let's see, this would be like 1/5 minus 1/6. The next one would be 1/5 minus 1/6, right? I'm just taking like first element of this and subtracting it from the first element of this, then the second element of this, subtracting it from the second element of this. I'll line them up just to make it a little more clear, right? Cool. So 1/5 minus 1/6, 1/5 minus 1/6, 2/5 minus 1/6, 0/5 minus 1/6, 1/5 minus 1/6, and lastly 0/5 minus 1/6. And I'm writing that in Python, but that's just, right? So it's just saying, right, hopefully I've said it a million times, but it's just finding the difference between what we observed, right? Our actual table, like we rolled the die and what we observed versus a perfect die. How different are those distributions, right? And then this last line is saying, well, it's taking the mean of something, but let's look at what it's taking the mean of, right? Y squared. So it's taking all these and squaring it. And if we were in, in-person section, I would ask people why we're doing that, but we're not in person. So, and I'm recording this, so I'll just say, basically, you can take a minute to think, right? Like you can pause it, but it's because notice how some of these subtractions, right? So some of these terms in the array are actually going to be negative and some of them are going to be positive, right? But what we really care about is like, how different is it, right? So if you think of it, we don't care, at least not right now, about whether it's different, like positive, like higher different or lower different. We just want to see like how different it is, right? And so if you think about it, if we didn't square it, right? So this is squaring it, but if we didn't square these differences, the negatives would cancel out the positives, right? So like if this, I know that it's like not, don't compute it in your head, but let's just say like, pretend, what if this term was like -1, this term was -1, this term was -1, but this term was 1, this term is 1, this term is 1, right? The total difference, right, would be 6, right? Because it'd be like, this is different by 1, 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 but the negative ones and the positive ones would cancel out when we summed it, right? And so that's why we square it, because when you square the negative numbers, right, they become positive. We could also take the absolute value. That's actually a thing that people do a lot. Like that's just an alternative version, right? You could take the absolute value or you could square it. Either of those operations takes the negatives and turns them positive so that when we sum, the negatives and the positives aren't canceling out and we're actually getting like the total, deviation, the total amount that our observed probabilities deviate from a fair die. So yeah, we square it to get rid of the negatives, and then we take the average. So this is, at the end of the day, it's taking the die probabilities that we observe, and it's taking the probabilities of a perfect, fair die, and it's subtracting them, seeing what the differences are, but not caring about whether it's negative or positive, just how far is it, right? If it's negative, 0.5, or if it's positive 0.5, we don't care. We just know that either of those are 0.5 away from like fair, right? So square it to get rid of the negatives, and we take the mean. So it is the average amount by which our probabilities that we see, right, our sample proportion, these numbers right here, differ from a perfectly fair die. So if you think about it, like, yeah, it's just making like another table here, like, I had to do this too. Great. So we could do fair die, fair proportion. We could say 1/6. 1/6. 1/6 is like 0.16, thereabouts. It's like that. Right, and so like this table might make more sense to people, is like really what's happening here, right, is we're taking, this is the proportion we actually saw, this is the proportion we expected, and like how surprised are we, kind of like, this one is higher than what we expected. We expected to get, 16.6% ones, but we actually got 20%, versus this is lower than we thought, right? We expected to get 16.6% fours, but we actually got 0%, right? So yeah, that's what's going on here. We're just seeing how surprised we are by this when we expected this. Cool. All right. Sorry, that was long-winded, but that's like super important. Test statistic, right? Notice how our whole function here is called mystery test statistic, right? So test statistic is just something that takes as an argument, as input. It just takes like, what did you actually see, right? And then it computes like, how weird is that relative to what we expected, right? That's, to me, that's all a test statistic is, right? And meaning like, if it's, say it's like perfect, say we actually rolled the die 6 times and we actually got each face once. Well, that would be like the least surprising possible outcome, right? Because that actually would be like, we expected 1/6 for a fair die and we actually got 1/6. So in that case, the test statistic would be 0, right? Whereas if it was super different from a fair die, like if we rolled 6 times and every single time we got a 1, then the test statistic would be really high, right? So all that is just to say that like test statistic of 0 means like no surprise whatsoever, right? Whereas the higher the test statistic goes, that means more like, oh, this is weird. Like the test statistic is supposed to pick out things that are weird based on what you expected. So like the higher the test statistic, the more different it was from what you expected. When in this case, we're expecting a fair die, right? And that's because our null hypothesis was fair die. Okay. So now that we've done all that, again, it's the average squared difference between our observed phase probabilities and the expected phase probabilities, right? You can go through these like, you know, is it the average of the observed probabilities? No, because like this sentence doesn't take into account, like it's not, like this is just, this right here would be just like some summary of our rolls, but it's not a test statistic, right? Because a test statistic has to compare our observed probabilities with some expected thing, right? So again, like numeric value of the most frequently rolled face, you know, that is some sort of like statistic about our rolls, but it's not a test statistic because it's not comparing our rolls with something, right? Again, observed probability of rolling a 6 minus observed probability of rolling a 1 doesn't take the expected probabilities into account. The only answer here that actually compares, you know, our observed phase probabilities with the expected phase probabilities is B. So question 2, answer is B. Great. Now this is the big kahuna. This is the function that we're going to write that actually like simulates dice rolls, right? So it actually does what I've been talking about this whole time, and then computes the test statistic for those dice rolls, and then it rolls a fair die a bunch of times, right? And also compares that with the test statistic. And the point is that like a fair die, because it's probability, the distribution, like if you roll a fair die 100 times, and then you take the same die and roll it another 100 times, those won't be the exact same, right? So what we want to do really, like in a perfect world, is roll the fair die like 100 times, find the proportions, then roll it again 100 times and find the proportions, and roll it again 100 times and find the proportions, right? So we start to get this list of like, okay, when we roll the fair die, this is what the proportions look like. And then, right, once we have that, we have a bunch of examples of what a fair die would look like. Then we can roll our die and compare it, right? And say like, how weird does the distribution, how weird do the probabilities of each face for our die compare, how weird is that compared to, you know, this list where we know this list was generated by a fair die, right? And so that's the whole like thing of hypothesis testing really, is you have like what you would expect to happen if you know that the null hypothesis is true, and then like how weird is our outcome, right? And that relative to what the outcome would look like if the null hypothesis was true. And that right there is like, that is essentially the p-value. That's the thing that we care about. That's going to tell us like, I don't know, that's going to tell us if this die is loaded or not. Cool. So yeah, like I said, we're going to take this thing, it takes a data frame describing the probability distribution of a die, right? So you give it information about the die, right? You give it a table like this, and then it's going to test that die against a bunch of rolls of a die that it creates that it knows is fair, right? And so it returns false if it rejects the null hypothesis about the die, and true otherwise, right? So the idea there being like, and we'll see at the end that because it's probability, nothing's ever this easy, but true means like, oh, we failed to reject the null. Like we do not have enough evidence to overturn our assumption that it's fair, right? So if it returns true, that means failed to reject the null hypothesis. But if it returns false, that means like, oh wow, this is actually surprising. We reject the null hypothesis that the die is fair, right? Because it's like, if it returns false, that means like the rolls that you generated are too kind of like too weird to that we really think it's not fair, right? But again, it's statistics, so we never know whether it's fair or not because we can't roll the die an infinite number of times, right? You can only roll it a finite number of times and then say like, you know, that's what probabilities are. It's like, how weird is this? How, you know, I expected 1 to come up this many times, but it actually came up this many times. What are the odds that that happens just by chance, and what, you know, versus that it happens because someone loaded the die. Cool. So yeah, first line of code is we just create this table, but for a fair die, right? So what happens here is fair die. It's just a data frame, and this is one way you can create a data frame with values that you want. You just say pd.dataframe, right? Remember, pd means pandas functions, and then data frame. And then in the parentheses, you just give it a dictionary, right? And so what this is saying is that make one column called face, and in there just put range 1 to 7 exclusive, right? Remember, it doesn't actually include the 7. So this makes our range from 1 to 6, which is 1 to 7 exclusive, 1 to 6 inclusive, right? So 1, 2, 3, 4, 5, 6, and then converts it to a list, because remember when we learned ranges that if you just type range, it doesn't actually make each of the numbers. It's just a formula to create numbers. Whereas if we convert the range into a list using Python's built-in list function, then it'll say, all right, I'll actually make the list. I'll actually make a list containing 1, 2, 3, 4, 5, 6, right? And so that makes this column face. And then probability, right? It's not proportion. I should say here, in terms of like vocabulary, probability is like an abstract notion in a sense. Probability is like in a model, right? Meaning like in our model of a fair die, in our mental image of a fair die, each side comes up with probability 1/6, right? So that's why it's probability. So like when you see the word probability, that's sort of like almost this hypothetical probability. Whereas when it's an actual observed, like, oh, I rolled the die 6 times and I got 1 this many times, in this class and like in statistics in general, there's different words, but we'll call that like a proportion, right? Just to differentiate those two cases. I know it's a little confusing, but yeah, proportion is the word for like, I actually rolled the die and I actually tallied, I marked down what I rolled each time. And then, you know, I rolled a 5 like 1 out of 10 times. Then that's a proportion, right? Then the proportion is 1/10. Whereas probability is like a more abstract notion, like, oh, we expect the die. We expect the die, like if we rolled it infinitely many times, each side would come up 1/6 of the infinitely many times, right? We can't actually roll a die infinitely many times. Hence, it's a hypothetical quantity. That's why we call it a probability instead of a proportion. For the sake of this, right? Cool. So again, we're making a fair die data frame. So we have face, and that's just 1, 2, 3, 4, 5, 6, and then the probabilities are all even. Right? So this right here, this line, creates a data frame containing all the information the computer would need to know about a fair die. Cool. And we display it. So when we run this, yeah, we'll see, yeah, phase 1, probability 1/6, phase 2, probability 1/6, right? That shows we've created our data frame correctly. Now we define some helper functions. This one right here is kind of good to know because this is saying like seed the random number generator. And that is like, you know, I don't know how to explain it very well, but computers can't actually generate truly random numbers. Random numbers are actually, like truly random numbers are actually extremely hard to generate. So it generates what are called pseudo-random numbers, which is like it uses some very, really, you know, complicated, messy formula to create numbers that look random and can be used as if they're random numbers. But since we're auto-grading, we actually need like your random numbers to like all be the same, right? Meaning like, oh, if you draw a random number, we can't really auto-grade if all, you know, 180 students generate different random numbers. I mean, we could, but it would be difficult. So what this is doing is it's just saying seed it, meaning in your formula that generates the random numbers, just put 1948 in first. So like plug 1948 into the pseudo random number generating equation, spit out the first number, and then spit out the second number, and spit out the third number, right? So that means since we've set this on everyone's computer, everyone will generate the same sequence of random numbers. If we didn't do this, the problem would be that instead of 1948, it would seed the random number generator. It would just take the time on your computer, like in milliseconds, and that would be the seed. So then everyone would have different random numbers based on the millisecond they ran their notebook in. So that's just so you know what that is. Simulate roles, right? So these are helper functions like Chris talked about in lecture, and simulate roles is a helper function that just says, okay, give me the number of rolls I should simulate and give me the die that I should roll that many times, right? So again, anytime, it might seem abstract, like how can you give a die into a programming language? Like it's not a physical die. So anytime we say that, really we mean like this table, right? This data frame that represents the information about a die so that it can simulate it, right? So we give it a number of rolls, we give it information about the die, and then it uses np.random.choice, which we've used before. And it just says, okay, pick one of these faces of the die. The probabilities of each face are given in the probability column, right? So meaning like it'll look here, P is the argument to np.random.choice that says like, okay, how likely, what should be the probability that I pick the first one? What should be the probability that I pick the second one, right? So give it this, and then we give it the faces, and then size just says do that however many times, do that n number of times. And in this case, it's number of rolls, right? So kind of like reading it in English, it's saying randomly choose from the die's faces with these probabilities this many times. Cool. And so it just returns that. It just returns a big list of outcomes. So like if we wanted it to roll a fair die 5 times, it could return like, 1, 5, 6, 5, 2. That would be like the sequence of rolls. 0 to 1, then a 6, then a 5, and then a 6, and then a 2. Proportion of total is just how we go from like that list of rolls, right, to make an actual proportion table like we made up here, right? Like notice here's the list, right? So here, this would be the outcome of like simulate roles, right? So simulate roles would generate this list of the actual outcomes. Then we want to generate this table which has the proportions of each number, right? So that is done by this proportion of total. And all it does is it says, okay, so, sum up the number of times that face came up divided by the total number of rolls that you did, right? So I should be a little more clear that basically it takes in a face, right? It's the face that you want to know the proportion of, and then all the rolls. And it just says like, so, you give it this list and you say, I want to know the proportion of 3, right? And so there you would send it faces 3, and roll outcomes is this highlighted list. And it would say, okay, I'm going to count the number of times that 3 appears, right, twice, and then I'm going to count the total number of things 5 times, and then I'm going to divide them. So the proportion that it would return for 3 is 2, number of appearances of 3, divided by 5, total number of things. And so we can call that for like all the faces, right? We can call that for 1, for 2, for 3, for 4, for 5, and for 6, and get the proportions of all 6 faces out of any roll outcome that we have, right? Any sequence of roll outcomes that we have. And so compute proportions just combines those two things. It just says, yeah, given an array of roll outcomes, compute the observed probabilities of each face and return it as a data frame. So, in a format like this. So like I said, it just makes face, which is a range from 1 to 7, exclusive, so 1, 2, 3, 4, 5, 6. And then the proportions are just this. You don't have to worry about, how this works really, but it's just saying take each face and find the proportion of the total roles that are that face, right? So cool. That's all it does. You don't need to worry about it. This is like this apply thing is kind of tricky, but it's just saying go through each thing in this, right? In this case, go through each face in the face column and apply proportion of total, meaning run proportion of total with that face and then return that table. Cool. Finally, there's the main function, right? This does everything we've been talking about so far. It takes in a data frame, actual die with information about a die, right? So this is the die that we're testing to see if it's phony, right? That's the die we want. We're like, I don't know if I want to bet my money with this person and their die. I first want to check their die to make sure it's fair, right? So that's actual die. Then what it does is it simulates rolling this actual die. Oh, that should be 10, but that's fine. These numbers are a little off because it's from the Berkeley class, but simulates rolling this actual die 100 times and computes the test statistic for these simulated rolls, right? So meaning like it rolls the actual die. It doesn't know if it's fair or not. It just knows the probabilities. Well, that's tricky. I guess it doesn't know like the words like fair or not fair. All it knows is like you've given it a die with certain probabilities. So it's just like you've handed it a die, and it's just going to roll it 100 times and compute the test statistic from above, right? So it's going to roll whatever die you give it. It's going to roll it 100 times, and it's going to say, okay, how weird were those 100 rolls compared to a fair die? But now it's going to do something even more like smart, which is like, well, even if you think about it, even if you roll a fair die 100 times, it's going to look different from 16, 16, 16, 16, 16, 16, right? So it's going to do something smart, which is like, now it's going to take a fair die, right? Like an actual die that it knows it's fair. And then it's going to roll that 100 times, right? And see that, how weird that looks, right? And so it's going to do that simulation of rolling 100 die and computing the test statistic for those 100 rolls. It's going to do that 250 times, right? So at the end of the day, what we'll have is 250 like tables, right? Meaning I took this fair die and I rolled it a bunch of times and I computed a table, and I did that 250 times, right? So we have 250 tables, all of which we know were generated by a fair die, right? And then what we can do is we can take the one table, right, which is our actual die that we rolled 100 times, and compare them. Hopefully that makes sense. I would be like looking out into the class and seeing if there were confused faces or not here, but yeah, feel free to like just pause the video and email me if you have questions. But the idea is like we have, again, just imagine like someone sitting there with like a bunch of pieces of paper on their desk. They have 250 tables, and they're like, I know these 250 tables were all generated by a fair die. So those are like within the bounds of what could be generated by a fair die. And then I have the one table that's like the actual die. And then basically I'm going to say like, how different is the test statistic, right? So I get a test statistic for my real roll, but I also have a test statistic for all these 250 series of fair die rolls, right? And I'm going to say, how different are those, right? So yeah, in this case, like I said, the numbers are round because it actually rolls 10 times per simulation, but it does do the simulation 250 times. And now our p-value cutoff, 0.2, we'll talk about that in a minute, but let's go into the code first. So roll outcomes, right? So that does simulate rolls. We define that above as just, you give it a number of rolls and you give it the die, and it gives you a list like 5, 3, 2, 2, 5, 1, 6, 5, 2. It just generates the outcomes of the rolls. It simulates rolling a die a bunch of times. So we roll the die, we roll actual die a bunch of times, right? And we get that into roll outcomes. If you don't worry about this, if statement is just like, you can choose whether you want this function to print out information or not. I suggest you do because it'll show you what's going on. But yeah, it's just saying outcomes of this many dice rolls is, and then it prints the outcomes. And then let me make a space between these. Right, so that's like the first part. The second part is observed proportions, right? So now it converts those rolls, rolls we just simulated, into a table. That's all that's doing. It's converting a list of rolls into a table that says like face, probability of that face. Second face, probability of that face. Third face, probability of that face. Right? And again, this just displays that table. And now the third part is observed statistics. So that is we compute our test statistic for this table, this observed proportions table, right? So we say, all right, how weird was that roll that we just did compared to a fair die, a perfectly fair die, right? So now, and when I say fair die, like it really is, it's like our model, our hypothetical model of a fair die, right? That comes up 1/6 probability of each number. Because, it gets a little confusing, because then what we do is we actually, right, we create the simulated statistics list, and we run this is a for loop, and it just runs 250 times, right? And each of those 250 times, it computes simulated rolls, assuming null. It's kind of long, but it's important to get that because it's saying, assume the null hypothesis, right? Assume that the die actually is fair. Right, and we achieve that by passing fair die to simulate rolls. So now simulate rolling a fair die, right? So simulate the rolls assuming the null hypothesis of a fair die. Simulated proportions is, again, it just converts those rolls of the fair die into a table. Statistical simulation, that just computes the test statistic for that simulated roll of a fair die. And then this line, right, it's just append is the key word here. It just appends it to here. So we're going to get this list, right, with 250 test statistics. And then we'll be able to see like, all right, this is what test statistics, this is what the distribution of test statistics looks like, even for fair die, right? So we'll see the test statistics of the test statistic distribution for fair die. And then what we'll be able to do is, right, at the end of the day, is like take our test statistic that we got with our die where we don't know if it's fair or not and put it on that plot, right? So, you can imagine like the test statistic, if we are smart, like if the test statistic is an actual good test statistic, it should look like a bell curve, right? Like in general, like there's lots of test statistics for lots of different types of statistical tests you'd want to do. But in our case, like the test statistic should be a bell curve around 0, right? Because remember, the test statistic is how surprised we are. So if we're actually rolling a fair die, most of the time we should not be surprised. Otherwise, it's a weird test statistic, right? So the test statistic should be, well, I said a bell curve, but it's actually like half a bell curve because the test statistic can't be negative. So just think of it like half a bell curve with peak at 0, right? Most of the time the test statistic is close to 0, but sometimes it won't be, right? Sometimes, if you do 250 simulations of rolling a fair die, sometimes you'll get weird distributions. Like if you sat at your, desk and you rolled a die like 250,000 times, like if you rolled a die 1,000 times and recorded those proportions 250 times, sometimes you get really weird things. Like sometimes you get like, wow, I rolled like 20 threes in a row, right? That's just how probability works. Take out a die and roll it a bunch of times and you'll see like, you'll get weird patterns because probability doesn't really work the way that our brains think like, oh, random means like uniform. Random means like, oh, I roll it once and I get a 5 and I roll it the second time and I get a 6 and I roll it a third time and I get a 4. And then a 3 and then a 1 and then a 2, and that's great because I rolled it 6 times and I got each separate face 1 time. But really, and that's not how probability works, right? Probability works like it'll generate things that you think are patterns but are actually just generated by randomness. Meaning, yeah, you'll get some simulations that you're doing here where it's like, oh, that's weird, I just got like all 6s. So that will have a high test statistic, but that won't happen often, right? Most of your trials, test statistical will be close to 0 because you're rolling a fair die and you're testing it against a perfect fair die, and so test statistics should be close to 0, right? But so now we get to the kind of punchline of the whole lab, which is that we compute the p-value, right? P-values are like, what's the word? Dangerous territory, because p-values are like how science academia works. Like basically you just do a big experiment, right? You spend months and months, sometimes years, decades, and then you put your data in and you compute a p-value, and then basically if it's less than some cutoff, in science it's usually 0.05, it's completely arbitrary. It's just something the scientific community like chose by tradition, by norm, and you just say like, oh great, my p-value is 0.02, so that beats the threshold, so now I can publish this paper in the top science journal. Or you get a p-value of like 0.08, which is not low enough, and then it's like, well, I gotta throw all this out technically. I mean, that's why you get like, it's called like p-hacking, where they're like, what if we took out some weird data points until we got a p-value that would let us publish, right? That's bad because that's not actual science. That's just trying to get published in a journal. Anyway, yeah, that's what we're doing here. Is we have one data point, which is our actual, test statistic from our actual roll of actual die here. And then we have 250 data points where each of those is a simulated roll of a fair die. And we kind of say the p-value is just how many times, here, let me highlight this. How many times is the simulated statistic, right? So simulated statistic is the simulated roll of a fair die. It's the test statistic from a simulated roll of a fair die. How many times is that like bigger, like more surprising than the actual observed statistic, right? Remember, just like if you remember one thing from this whole section, it's that this test statistic is just how surprised are we, right? So if you think about it, the number of times that like the observed statistic, like the observed statistic, the lower it is, the more we're like, I don't think it's loaded. I'm not surprised by this outcome. It seems perfectly normal for a fair die to produce that outcome, right? So if you think about it, like if the observed statistic is less than the simulated statistic a bunch of times, right? That's what like if you reverse this order, it's saying like, I'm even gonna reverse it, right? Because that's, whoops, that's actually logically equivalent. It's just saying like, if our observed statistic is lower than the simulated statistics, right? We have a big list of 250 simulated statistics, and it's like, how many of those 250 is our observed statistic lower than it? That is like good evidence for the null hypothesis, right? That it's fair. Because if, how do I put it? So fair, yeah, surprise of 0, right? To test statistic of 0 would mean like, oh, it literally came out 1/6 perfectly. So the more times our observed statistic is like close to 0, right? Meaning it's less than the simulated statistics. The simulated statistics are what we just talked about, where it's going to be like a half bell curve, right? Where the peak is at 0, and then as you get further and further from 0, it's less and less likely that you get a simulated statistic that's like high. So yeah, I'm just trying to, I wonder if I can even, yeah, let me just like get a bell curve and like gesture with my mouse what I'm talking about, right? So that was dumb. Great, here we go. All right. So take this bell curve, right? And it's like cover up this left side. So I'm putting my hand on the screen and I'm covering up the left side. Right? Just looking at the right-hand side, that's what the distribution of test statistics look like, right? The peak is up here, right, towards 0, right towards the middle of the x-axis. Whereas, like, you know, you roll a fair die, like I said, sometimes they'll get weird outcomes. Those will be out here, right? Those will have high test statistics. So like, our test statistic is created so that the ones that are closest to the fair die that we expect, 1/6 probability of everything, the test statistic for rolls of the die that are close to fair will be here. That's why there'll be a peak here, right? And so all we're doing is we're making this curve, right? We're creating this curve by creating 250 rolls of the die. And then what we do is like we put a big red dot somewhere on this right-hand side of this graph, right? And that big red dot is like the test statistic that our actual die generated, right? So if the big red dot is like here, that's evidence in a sense that it is fair, right? Because 0 is like what the perfect fair die, right? A test statistic of 0 means it came out perfectly fair. And then, but if we compute the test statistic for our roll of our actual die, and it comes out like way out here, like the red dot is like out here, the test statistic is like, you know, 4. That's very strange, right? Very, very few times. The curve is low here, and that means like very, very few times the fair die produced a test statistic this high, right? So like, it is very unlikely that a fair die produced something that's this far out, that has a test statistic that's that high, right? And so that's all we're doing here, right? Going back to the, wow, I lost it. Here it is. Great. Going back to the lab, that's all that is happening here. We're just saying, like, you know, put a red dot down and see what proportion of all of that curve is below it, right? If there's a bunch below it, then, right? So meaning like if the red dot is like way over here, that means like almost it's bigger than almost all the test statistics. But if the red dot is here, then it's like smaller than almost all the test statistics, right? And so, cool. So that's all that this is doing. It's saying how often is the observed statistic less than the simulated statistic. Cool. And then we just have a cutoff, right? In this case, it's 0.2, but like I said, in science, it's like usually 0.05, but on your lab, it's 0.2, meaning any p-value less than 0.2, going back to this curve, if we place our red dot, right, representing the test statistic of our actual die, any red dot that's 0.2, right? So like here's like 1, here's 2, here's 3, here's 4. So 0.2 would be like here. So if the red dot is like here, wow, sorry, I've been talking about it backwards. What I've been talking about basically is like the 1 minus the p-value, right? So just take everything I said and reverse it, meaning like if the red dot is way out here, we say that's weird and we get a low p-value. Like what's, you know, you can think of it like what would be the probability of getting that test statistic given a fair die, right? Remember, that's what we've been doing this whole time. I'm sorry. So we're putting a red dot down, and we're just saying like everything out here, super weird, right? Everything out here, you'd be very suspicious. Like, how did the die produce that weird of a test statistic? Like, I rolled the fair die like 1,000 times, and that never happened, right? So, whereas here, so we're seeing, you know, how like the p value is essentially just you put the red dot down, you plot the test where you pick the test statistic of your actual die, find it on the x-axis, and plop it on the curve there, right? And however high it is, that's your p-value. So if it's really low, right, like the probability is like way out here, that's the only time we reject the null hypothesis that it's fair, right? We say like, oh, it's just so far out there, right? This y-axis, the probability is just so low that we reject it. Otherwise, like if it's over here, if it's like up here, probability of that is like really high, right? It's like one of the highest probabilities to get a test statistic up there, so we don't reject it. All right, so let's run it, right? So we take the fair die, right? Remember we defined fair die up here. It's just a table describing a die where every face has the same probability, 1/6. And let's simulate it. And I did display rolls equals true as an optional argument to the function, which will display like what's going on inside. Oh, that happened because I haven't run this. It's gonna, oh yeah, you need to like run all these. I just like skipped over them, but you need to like actually run these code cells. It's my bad. Yeah, so look, simulate rolls and test. So this is like everything I've been talking about. Finally, we get something concrete. So here, it takes the app. We're now testing a fair die, right? So we're saying, what happens if I actually test a fair die? What happens if I put a fair die in here? So it takes the fair die you gave it, but it doesn't know that it's fair. You're just giving it a die and it's testing it. It doesn't care what the die is. We just happen to pass it a die that we defined to be fair, right? So we pass it a fair die. It rolls it 10 times and it gets 3, 2, 6, 4, 2, 3, 4, 3, 4, 5, right? And it computes this proportion table, right? Where actually it's interesting, it didn't get a 1. So that's a little weird, right? That might bump it like slightly up, like probably, you know, getting 1 0 times, it's like pretty different from 1/6, right? So remember our test statistic is looking at how different our actual observed distribution is from fair die, perfect 1/6. So that will probably push it out a little bit that we didn't get any 1s, right? So we didn't get any 1s and we got more 3s and 4s than we expected, right? Like double, right? Because we expect to get 0.16, but in actuality, like 3 out of 10 times, even though we expected like 1.6 out of 10 times, so 1 or 2, we actually got the value 3 times, right? 1, 2, 3, and we got the value 4 3 times. 1, 2, 3. But yeah, those are kind of the outliers, right? That was random roll, and we get 1 0 times, but we get 3 and 4 3 times each. And now we see that the outcome, right, it returns true. Going back up to our little key of what the function will return, it returns false if it rejects the null hypothesis about the die, and true otherwise. So true means it does not reject the null hypothesis. It means we fail to reject the null hypothesis that the die is fair, right? So it's actually kind of a, how do I put it? It's kind of a lenient test in the sense that like this is a bit of a weird, you know, die. Like if you took a die from your friend and he's like, and they're like, oh, I promise, like it's fair. But then you rolled it like 10 times and you didn't get a 1 at all, ever. Or say you ran it 100 times and you didn't get a 1 ever. You'd be like, that's kind of weird. Maybe they might use this to like bet against me, like go to the, you know, bet with other people at the gambling party or whatever that, you know, oh, it's not, hey, I bet you all $1,000 that Jeff's not going to roll a 1, right? So you may think there's something suspicious there, but this statistic basically says it's not suspicious enough, right? It's still like close enough on this kind of left side. Remember, we're covering up the actual left side of the graph. So it's kind of close enough to this like peak of our test statistics from rolling fair die that we're gonna not reject it, right? But we can run it again. We can run it as many times as we want now, right? And we can say, okay, let's just run it again with a fair die, right? So this time we don't get any 3s, but we get more 4s than we expect. And yet we still get true, right? So it still fails to reject. So hopefully maybe people are starting to see what's going on, get another true, even though this time we got 1 4 times. Before we didn't get 1 at all, now we got 1 4 times, but we got pretty much all the other ones less than we'd expect, right? Just keep running it. Aha, so this one, we actually got a false, which means it said, oh, this die, right? I just, from rolling it 10 times, those 10 rolls came out so weird that I actually, like, its test statistic is so different from the test statistics I got rolling a die I know is fair 250 times that, yeah, I'm gonna reject the null hypothesis, and I'm actually gonna say, no, I don't think this is a fair die. Just notice, we actually gave it a fair die, right? It's just because of randomness. Like, we gave it a fair die, but the rolls were so weird that it said, I don't think this is fair, right? And that is the like lesson of this section, of this lab, is that because of randomness, sometimes even a die that actually is fair will look unfair, right? And it all has to do with the p-value cutoff, right? We're only returning whether our p-value is bigger than our p-value cutoff, right? Which in this case is 0.2. Right, so we gave it a fair die. It rolled it 10 times, but it never got a 1. And it got a 5 4 times. So, and it never got a 4. So it's kind of like, you know, the thinking here, you know, in a sense, is kind of like, oh, I think this is loaded so that 5 comes up a ton, right? But 1 and 4 never come up. So you're like, oh, wow, the game I was going to play, 1 and 4 are the bad outcomes, and 5 means jackpot. So yeah, my friend was definitely cheating with this one, right? That's what you might think if you saw this, but actually we know that it's a fair die. So it's just because of randomness. And yeah, that's how we answer this question, which is like, using your knowledge of hypothesis tests and interpretation of the code, what's the probability that simulated observations and test returns false, even though its argument is fair die, right? So what happens is that's literally what the p-value cutoff is, right? It's saying, all right, I'm just going to make my test some strictness that 0.2 with 0.2 probability, it's a false rejection, right? So 20% of the time, even though like we're calling it with a fair die, 20% of the time it's still gonna think it's not fair, right? And that's just because it's random. You can never actually know. So this p-value cutoff is like a subjective threshold. That's kind of like where subjectiveness comes in statistics and probability. It's just like, you know, journals, scientific journals, like I said before, they set a p-value cutoff of 0.05. And that's literally just the scientific community saying like, well, okay, we're gonna make our test strict to the level that, like, you know, 95% of the time it will detect it correctly, but 5% of the time it won't, just because like that's just because randomness, like bell curves, right, work the way that they do. Meaning bell curve, right, like most of the time you're going to get stuff close to 0 on your test statistic. Sometimes you're going to get stuff out here, even though it's a fair die, right? All it's saying is just like, at what point do I say like, that's just too weird. I know a fair die could have produced it, because a fair die could produce any outcome, right? But at what point do I cut it off and I just say, no, that's too far out, right? That's too far, you know, out from the peak of this test statistic curve, that I just say, no, I think that that's too weird. We reject, you know, the null hypothesis that it's fair, or that there's like no effect, right? So in this case, that's 0.2. And that just means like, if you want to kind of translate it into this curve, it's like the point at which only 20% of the area under this curve is to the right of it. That's just, I mean, you don't really, it's like not, I don't think the number is like that important. It's just that, you know, it's saying a fair die could produce any result, right? Because it's random. The only thing that makes it fair is that, like, oh, if I rolled it an infinite number of times, which you can't do in real life, but as I roll it more and more, the fair die will start to look more and more fair. You know, like it'll start to look more and more like 1 6 1 6 1 6 1 6 1 6 1 6, whereas a not fair die will start to look like whatever it's weighted towards. So you make a cutoff, right? And you say, if the test statistic for the die you give me is to the right of it, I'm just like, that's too far out, and I reject the null that it's fair. Whereas if the test statistic is here, close to, you know, most of the test statistics that I got when I rolled the fair die, then, you know, I'm going to say, all right, I think this one's fair too, right? So this p-value cutoff, it's just a split. It's just a line you draw on this graph, and you say, that's where I'm saying, like, you know, that's where I'm saying. So in science, it's like a fairly tough, you know, what's it called? Standard of evidence, meaning in science, you have to like provide enough evidence that the null hypothesis, which is again no effect. Like if you have like a drug and you're testing it and you're trying to publish in a journal, like, hey, my drug works, you have to like show in a clinical trial that, like, you know, people say the distribution of people who got better after taking your medicine versus the people who did not is like so different from if it was just random, you know? Like you would compute the test statistic of like, what would it look like if people just randomly got sick or didn't get sick? And then you compute the test statistic of like, what's the test statistic of people who took my medicine, right? And if the test statistic of people who took your medicine is like way out here, you say, okay, I don't think that happened by chance. I think that the medicine's actually doing something, right? So in the science community, they just say that cutoff is like 0.05, which means 95% of, so, you know, think of all the area under this curve, and then like 95% of the area is to the left of that cutoff, and 5% is to the right. So that's like way out here, right? Okay, just trying to drive that point home, that p-value is a cutoff where you just pick a point and you say, if the test statistic is that far from what I expect, which is 0, you expect a test statistic of 0, then I'm going to reject the null. Otherwise, I think it's just the null. Cool. All right, and then real quick, because I know I'm going over time, going back to this. So again, what's the probability of false now that I've done that whole thing? Well, the p-value cutoff is 0.2, right? So again, all these observations here were generated assuming the null was true, right? So even when the null is true, you're putting the cutoff so that 20% of even the true test statistic, even the test statistics generated when the null hypothesis was true, are to the right of it. So the probability of false is just the p-value cutoff, right? Meaning this is saying like the probability that that our little test code rejects the null hypothesis, even though we literally passed it a fair die, so we like happen to know that the null hypothesis is true for that die, it's still going to say, no, it's false 20% of the time, because it can't. The only way you'd possibly get like perfect statistical detection, right, is if you could roll the dice an infinite number of times. But you can't, so we use this as kind of a trade-off, right? 0.2 is kind of like lenient. Scientific community uses 0.05, like emergency medicine. More strict than 0.05, right? It's like 0.0001. So like to say like, oh, this intervention is working, you really have to, it really has to be like, wow, that test statistic is of the outcomes that you got with your medicine is so different from like the test statistic that would happen just with people getting sick and not getting sick. All right, so the probability of false is 0.2. That's the answer to question 3. That's just the cutoff. Why is it not 0? And you can read that. This is kind of a giveaway because it's just like computers sometimes make errors. Well, no, that's just this. It's a statistical thing, not a computer thing. Because probabilities are always 0. That's definitely not true. So it's because, yeah, the p-value is the probability that you would obtain this observations test statistic if the null was true. Just, you know, read C. The answer is C, but like read it on your own time. Question 5. Now this takes like a minute, and it's just saying, all right, run, simulate, rolls, and test on the fair die 300 times, appending each result to test results once it has been computed. Yeah. So we can make this test results list, and it says 300 up here, but the code that you have, the starter code, says 150. Don't worry about it. Run it 150 times or 300 times. It should still be fine. I'm going to run it 150 times for speed. So it's saying run the test simulation 150 times, and then we're going to store each of the 150 results in here. And what we're going to do is just going to make a for loop that runs 150 times. And each time we are going to call a function we made up here, simulate roles and tests. Simulate roles and tests, right? And what does simulate roles and tests take? It takes a die, and then it takes display roles. But don't do display roles equals true, because it will display your roles like 150 times, and it'll just might crash your computer. So just call it, just give it a die, right? So run simulate roles and test on the fair die 300 times. Give it the fair die. Cool. And then, oh, sorry, I should say result, say test result equals simulate roles and test, right? Test result, if we remember, this function returns true if, I can't even, I have to remember my key. It returns false if it rejects the null hypothesis, and true if it fails to reject the null hypothesis. So here, it's going to run 150 times, and test result will be true whenever it fails to reject, and false when it rejects the null, given it's a fair die, right? So, oh, whoops, I'm sorry. Because once we get test result, we have to put test result into append test result to the test results list. So test results dot append test result. Now that's the code for it, right? This is what you had to fill in for the lab, these two lines, because it's saying, of course, it's going to run it 150 times. This, if you remember, is just means every 10 times through the loop, just update us on the progress, right? Every 10 times, just print on simulation num out of the total num. And now this is saying, run the simulation with a fair die, store the result and test results, but then append that test result to the end of our big list of all 150 test results. Right? Cool. So we run it. It takes a little while. I probably should have done class announcements in this time, but it'll be worth it. I promise. I'm just gonna stare at the screen awkwardly. Someone asked me to include the cat in these, so here I'll show you. Here is the cat. He has a little igloo, and he's asleep in there. Hey, you got an audience. Yeah, so that's the cat. That's your entertainment while this runs. He's very old, and he sleeps a lot in his igloo, which for whatever reason is very flat but comfortable. So yeah, there's your weekly Hugo appearance, right? That's Hugo, Hugo. He's named after Hugo Chavez, if anyone's familiar, and it's a whole story that I can tell you. But cool. So we have run the simulation 150 times, right? And we have this big blob of falses and trues, and it looks like more trues than falses, which is good, right? Because we're running it with a fair die. So most of the time, again, hopefully 80% of the time, it's true, right? And 20% of the time, it is false, even though we know that the null hypothesis is true. So what we're gonna do is I just looked at it, but question 6. So question 5 is running that and then showing, the truths and falses for the 150 simulations. And now question 6 is just finding out what proportion of these are true and what proportion are false. So this is the actual proportion false, right? And we want you to fill in the code, but this is kind of not statistics related, but more just knowing the function in NumPy, which is all you need to do is you need to say np.count non-zero. If I had more time, I would explain that function, but it's just saying count the number of times that this is true, whatever I'm about to give it, right? And then I say test results np. So notice I converted to a NumPy array. So up here it's a Python list, but then here I converted to a NumPy array so that we can use this nice NumPy function, count non-zero, and I just say test results NP equals false, divided by len, right? Divided by the total number of things in test results NP. Right? So this is saying count the number of times that test results NP is false equals false, right? So test the number of times that the things in this list, right? Then there's a false element in this list, and then divide by the total length of the list. Cool. And what do we get? We get 0.246 repeating, right? So that's kind of close to 0.2, which is what we expected, right? That even though the lesson here, the point of all this is that even though we're running it, we know that it's a true die. I mean, a fair die, right? We're literally running the simulation a bunch of times, and we're sending it a thing that we've defined to be a fair die. Despite that, it's still rejecting the null hypothesis that it's fair, like 24%, 25% of the time, right? Which is showing that like these, even when you make the cutoff, right? So even when you make that cutoff, it's still not perfect because these are all like simulations. Like if I made the number higher, right? Like if I made, if I made like roles per simulation more than 10, it would be more accurate, right? And if I did more than 250 simulations of the null hypothesis, right? So 10 is the number of rolls it does anytime you say like simulate dice rolls. Num simulations is the number of times it assumes a fair die, runs the simulation, and then computes the test statistic, right? That's how you make 250 data points go into making this bell curve. And lastly, like if I made this number of simulations, so that's like on top of it, that's like do all that 150 times. So if I made that higher, it would also work, but it would just take a long time. The point is like if num times test simulations was like 1,000 and you did 100 rolls per simulation, you did 1,000 simulations under the null hypothesis, it would be like exactly 20% would be false and 80% would be true, right? Because that's our cutoff. We're saying like, all right, if things are weirder than 80% of the roll sequences I did with a fair die, I don't think that's fair. You know, whereas if it's, you know, so if it's, if I roll a die and it's like only weirder than like 10% of them, I'm fine with that because like, you know, a lot of the fair die rolls were around here. You know, this is like, say like this is 10%, this is 20, this is 30, 40, 50, 60, 70, 80 is like out here, right? By the time that you are weirder than 80% of the rolls, the simulated rolls of the fair die, you start to think maybe this isn't, you know, this is not likely to happen if the die is fair. So, whoops, that is AutoGrader code. So anyway, yeah, we saw that we would expect that even though we are doing the test on a die that we know is fair, we still get that it thinks it's not fair 20% of the time because that's the p-value cutoff. And we actually like, you know, ran it a bunch of times with a fair die, and we saw that it actually rejected it like even more time. It rejected it 24.6 repeating times, even though, you know, it should only reject it 20% of the time, but that's because of time constraints. But yeah, if you have nothing to do during self-quarantine and you want to set this to be like 1,000, set this to be 100 and set this to be like 1,000, you'll get that essentially like you'll give it a fair die 1,000 times and it will say, oh, no, I failed to reject the null hypothesis. I think this is fair 800 times, but it will say, actually, I think this die is unfair, even though you know it's fair 200 times because that's your p-value cutoff, right? Cool. And that's it. Submit by a Jupyter Hub, right? So that's like, you go back here, go to the assignments tab in your Jupyter Hub, you go to lab 6 and click submit. And Then go back, where is it? Here. Now go back to it, click File, download as HTML, right? Open that HTML document, click Control P to print it. It's a PDF. I'm gonna save it on the desktop. Jeff Lab 6.pdf. And then go to Gradescope and submit this. Right now you have a little PDF with your answers. Cool. So go to Gradescope, click Lab 6 and submit it. So great. Thank you all for bearing with me. This was a tough one. The difficulty is definitely ramping up. And I tried like explaining, you know, this test statistic thing, this bell curve thing a lot, but like I definitely anticipate, you know, people coming to me with questions. So yeah, that's all. Thanks.